እንዴት ናችሁ ተማሪዎች? ሰላም ነው ሁሉም? በቤታችሁ ነው ያላችሁት? እያነበባችሁ ነው? Okay. We will continue the new lesson today. It is about ideal gas equation, what we have learned it earlier. Here, ideal gas, hypothetical gas that obeys the gas laws. Real gas only obeys ideal gas at high temperature and low pressure. Don't forget, okay? Real gas only obeys the ideal gas law at high temperature and low pressure. Under this condition, particles are very far apart because the temperature is very high. Here we have some laws, okay? The first one is Boyle's law, the second one is Charles' law, and the last one is Avogadro's law. We have seen it earlier, okay? The last class we did about the relationship between volume, temperature, and pressure. Here today we look about the ideal gas equation, which is given here. PV is equal to nRT, where P is pressure, V is volume, N is the number of mole, R is ideal gas constant, and T is temperature. Okay. Ideal gas law can be calculated at 1 atm. The pressure, volume is 22.4 liter, and N is the number of mole, which is 1, and temperature is 273 Kelvin. So finally, it gives this number. Okay, for calculation, we always use 0.0821 liter atmosphere per Kelvin dot mole. Calculates the volume in liters occupied by 4 moles of CO2, carbon dioxide, at temperature is given, and pressure is 1 atmosphere, ideal gas law. Equation is ideal gas constant is given also, which is PV gives nRT. Calculate the volume. Okay, so after rearranging the formula, volume becomes nRT over P, which is number of mole is given, it is 4 mole. Ideal gas constant 0.082, and the temperature is 273 Kelvin divided by how much? The pressure is 1. It gives you 89.455 liter. Do you get? Thank you. So you have to use this ideal gas constant for your calculation. Graham's law of diffusion. Graham's of diffusion states that at constant temperature and pressure, the rate of diffusion of gas R is inversely proportional to the square root of density or mass. The square root of density over mass, meaning R1 over R2 can be given the square root of M2 over M1, or the square root of density over density 1. So rate of a gas is inversely proportional to the square root of mass or the square root of density, which is given here. So rate is inversely proportional to density, the square root of density or mass. The formula can be given, R1 over R2 is equal to the square root of density 2 over density 1, or R1 over R2 is equal to the square root of M2 over M1. It's also related to the time, okay? Rates and time are inversely proportional, okay? Where T1 and R1, M1 are initial, T2, M2 and R2 are final. let's go to the exercise. Which gas will diffuse faster, hydrogen or oxygen? Mass of hydrogen is 1 and mass of oxygen is 60. Okay, here we have oxygen molecule and hydrogen molecule. So which gas do you think diffuse faster from hydrogen or oxygen? According to Graham's law, gases that have low mass diffuse faster than gases that have higher mass. Due to this, hydrogen, here we have 2, so 2 times 1 is 2 gram, but oxygen 2 times 16 is 32. So which diffuses faster? Oxygen, okay? Which diffuses faster? Sorry. Which diffuses faster? Which is hydrogen. What is the relative rate of diffusion for the above gases? Meaning R of hydrogen over R of oxygen gives us mass of oxygen over mass of hydrogen. Inverse relation, okay? So mass of oxygen is 32, mass of hydrogen is 2. It gives you 16, then finally becomes 4 over 1. So rate of hydrogen is 4 times rate of oxygen. So the relation is like this. Okay, do you get? Okay. The liquid states. We have seen it. Liquids have definite volume, indefinite shape. They take the shape of this container. They are in constant motion, and the particles in liquid are some slightly far apart and compressible. The attraction with the liquid particle caused by intermolecular force like dipole-dipole force, London dispersion force, and hydrogen bonding. Liquids are more ordered than gases because of strong intermolecular forces that we have seen. Energy change in liquids, the process by which liquid changes to gas is known as vaporization. Evaporation is the process by which liquid molecules break freely from the liquid surface and enter the vapor phase. Evaporation explained in terms of energy possessed by the molecules. In an open container, evaporation continues until all the liquid enters the vapor phase. However, liquids are in closed container behave differently. When liquid gets energy with the process of evaporation, they change to gas. When they lose their energy, condense and becomes liquid. So in closed container, the vapors cannot escape. The reason why, because as the vapor concentration increases, some of the vapor molecules lose their energy and return to the liquid state that we call condensation. When they get energy, the opposite is also evaporation. So liquids and gases are like this, okay, given here. Evaporation when they get heat energy, and condensation when they lose air energy. The rate of evaporation of liquid depends on 3 factors. These are temperature, intermolecular force, and surface area of the liquid. As the intermolecular force increases, since the molecules hold each other, becomes closer, their evaporation increases, okay? Increases. Temperature increases, average kinetic energy of the molecules, and this increases the tendency to change into the gaseous state. Some liquids evaporate readily at room temperature, meaning at 25 degrees Celsius. Such liquids are said to be volatile. The volatile liquids have relatively weak intermolecular force of attraction between the particles. For example, diethyl ether, ethyl alcohol, benzene, acetone, and are volatile liquids. Non-volatile liquids have a little tendency to evaporate at a given temperature. They have relatively strong attractive force between their molecules. For example, sulfuric acid, water, and molten ionic compounds. Vapor pressure is the partial pressure of the vapor above a liquid. Okay, the vapor pressure of a liquid depends on temperature. At a given temperature, vapor pressure is constant. Okay, it is constant. As the temperature increases, the vapor pressure of a liquid also increases, which has direct relationship. Due to high rate of evaporation, vapor pressure depends on also strength of intermolecular force that I have told you before. The stronger the intermolecular force, the lower the vapor pressure will be, because fewer particles will have enough kinetic energy to overcome attractive force at a given temperature. For example, water and alcohol have relatively low vapor pressure. On the contrary, liquids with low intermolecular force have higher vapor pressure at room temperature. For example, diethyl ether, a non-polar molecule with relatively weak dispersion forces and has a relative higher vapor pressure. Boiling and boiling point. What is the difference between evaporation and boiling? How does boiling point depend on the external pressure? Boiling is the conversion of liquid to vapors within the liquid as well as its surface. It occurs when the equilibrium vapor pressure of the liquid equals the atmospheric pressure. When the equilibrium vapor pressure of the liquid equals the atmospheric pressure. So during this time, boiling will occur. During evaporation, only molecules at the surface escape into the vapor phase. But at the boiling point, the molecules within the liquid have sufficient energy to overcome the intermolecular attractive forces of their neighbors. So bubbles of vapor are released at the surface. The temperature of the liquid increases, the equilibrium vapor pressure also increases. Finally, boiling point is reached. Boiling point of a liquid is the temperature at which equilibrium vapor pressure of a liquid equals the atmospheric that we have seen earlier. Therefore, the lower the atmospheric pressure, the lower the boiling point also. So they have direct relationship. If the external pressure is 1 or 760 millimeter of mercury, the boiling point is called normal boiling point, when the pressure is this much and given here. For instance, when water boils at 100 degrees Celsius, when the pressure is 1 atmosphere, okay? Thus, the normal boiling point of water is then 100 degrees Celsius. So, where will water boils first? In Addis or Awasa? Why? Try to answer this question. Boiling of a liquid requires a certain amount of heat energy, otherwise the molecules cannot be broken. So the amount of heat energy necessary to boil about evaporation of a fixed amount of liquid at a fixed temperature is said to be heat of evaporation. So they have molar heat of vaporization and molar heat of condensation are equal and opposite, which means vaporization is endothermic process and condensation is exothermic process. Okay, condensation exothermic, vaporization is endothermic. The next one is about solid state. Solid state. When a solid is continuously heated, its order of crystalline structure is disturbed. The particles attain their freedom of motion generally, and melting takes place where the solid is converted to the liquid state. The temperature at which crystalline solid is converted to a liquid is known as the melting point. The temperature at which crystalline solid is converted to liquid is known as melting point. In contrast, when a liquid is cooled, the molecules becomes closer and the intermolecular force of attraction becomes stronger. Okay? When liquid cooled, molecules comes closer and the intermolecular force of attraction becomes stronger and stronger. The particles arrange themselves into a regular pattern in the liquid. The process is called freezing or solidification. Becomes what? Solid. Solid. Both melting and freezing takes place at the same temperature. Both liquid and solid phase coexist at equilibrium with each other at melting and freezing point. Melting and freezing point. We can see here, when ice melts, it changes to liquid water, and when liquid water freezes, it changes to ice. Both takes place at 0 degrees Celsius. At 0 degrees Celsius, okay? The amount of heat needed to convert 1 gram of a solid to a liquid at a melting point is called heat of fusion. Heat of fusion. The molar heat of fusion of molar heat of enthalpy is the quantity of heat needed to convert 1 mole of solid at melting point to liquid state. Liquid state, okay? For example, the molar heat of fusion of ice is about 6.01 kilojoule at 0 degrees Celsius, okay? This is the amount of energy needed to break the attractive forces in that solid at the melting point. Melting requires the supply of energy. Therefore, it is an endothermic process. Melting is an endothermic process, okay? During the process of solidification, an amount of heat equal to the heat of fusion must be liberated. So, solid, when it gets heat energy, it sublimes and changes to vapor. Sublimation is direct change of solid matter into gaseous state. The opposite is, or the reverse process is said to be deposition, which means when vapor directly changes to solid state, we call it deposition. So, molar heat of crystallization and molar heat of fusions are equal and opposite. During the sublimation process, heat energy is absorbed, but it is an endothermic process. Sublimation, endothermic process. Molar heat of sublimation is heat. Molar heat of fusion is the quantity of heat required to convert 1 mole of a solid to a gas at its sublimation point. So, molar heat of sublimation and molar heat of sublimation means the sum of both molar heat of fusion plus molar heat of vaporization. These two processes takes place at the same time. Phase change and energy change in solids. A phase change is part of a system that has uniform composition and properties. A state of matter represents a phase. A state of matter represents a phase. Most solid substances undergo 2 changes of status. A solid changes to liquid at melting point, and the liquid changes to vapor at boiling point. So, they takes place 2 changes of status. To understand the change, we'll consider the heating curve for a substance. Heating curve is a plot of temperature versus the uniform addition of heat. So we can see it just using the diagram, okay? As given here, heating curve, the vertical column represents temperature and the horizontal column represents the time in second. So when a substance is given, or a matter given, here up to the melting point begins, the substance is found in solid state. After boiling point begins here from B. Here we get the mixture of both solid and liquid substances. After the ending of melting, we get here liquid substance only. After reaching the boiling point, okay, here it is boiling point. Here you have melting point, okay. Here at boiling point, since liquid substance begins to boil, we get here liquid and gas particles. Then finally, after the end of boiling, all matters which are given here changes to gaseous status. We can see here. Initially, the substance exists in solid state. Meaning here. And then, when the solid is heated, its temperature rises A to B until it reaches where? Melting point. Point where it is at B. Then the temperature remains constant B to C. And all the solid is converted to liquid at point C. At point C, all solid changes to liquid, and all matters which are found here becomes liquid. Then a solid changes to liquid at melting point, and liquid changes to vapor at boiling point. Vapor to boiling point at melting point becomes liquid. Okay. A heating curve is a plot of temperature versus the uniform addition of heat. This can be illustrated hypothetical substances in which the temperature of substance is 1 on the vertical axis, and the passage of time during which heat is added to the substance is on the horizontal axis. The change in the temperature and phase of substances as it's heated, beginning with a solid continuing to the gaseous state as described. So, as temperature increases here, solid matter, solid changes to liquid, and when the temperature increases, becomes what? Gas. What we have seen here is when ice melts, and it changes to liquid. When liquid water freezes, it becomes ice, and the temperature coexists here, okay? The second one, when solid sublimes, it changes directly to vapor or gas. When vapor changes into solid, the process is said to be deposition. Sublimation is the sum of molar heat of fusion and molar heat of vaporization. There is phase change that we have seen earlier, and energy changes in solid. These are when a given matter gets heat energy, it absorbs first, and at its melting point, it changes to solid state. Then here we get the mixture of solid and liquid. After it here at point B, the temperature remains constant, B to C, until the all solid converted to liquid. At point C, the temperature remains constant, we said. The added heat energy is used to break the intermolecular force and disturbing the solid structure. At point C, phase change is completed. Okay, students, this is all about for today. Goodbye. Please read more and ask persons which are found nearer to you. Bye.